Hello, this is lecture 5 in my sequence of video lectures on robust statistics. This is really the first big payoff lecture where we begin to use the techniques that we developed in the previous lectures to actually get efficient algorithms for robust statistics problems, specifically robust mean estimation under bounded second moments. And as we'll see, the algorithm itself that achieves this, given our previous machinery, is actually very simple to describe. And in fact, we'll do the entire analysis just straight up today. So let's just jump in. So throughout this lecture, I'm going to be using a lot of notation from lecture 4, so let's briefly recall that here. So we're going to have a set of points S, which we'll denote as x1 through xn, and we're going to let gamma sub n be the subsimplex over n things. For any set of points T, let w of t be the set of weights, which are 1 over n for I and t and 0 otherwise. And then let fancy w sub n epsilon be the set of weights in the subsimplex, which are pointwise bounded by the uniform set of weights. So wi is at most 1 over n for all I. And moreover, the L1 distance to the uniform set of weights is at most epsilon. And then we're going to make the usual structural assumption about S, that S is equal to S sub good union S sub bad sum minus S sub removed, with the usual conditions on these three sets. We're going to let mu be the mean of the good points, and we're going to assume that the covariance of the good points is bounded by the identity. And recall this is a deterministic condition, but in lecture 4.5 we argued that after something like d log d over epsilon samples from a distribution with a bounded second moment, it suffices to solve this problem. And with that, we can now state the main result from lecture 4. The algorithm guarantees the following. It takes as input any set of non-negative numbers tau 1 through tau n, and any element w of the subsimplex. And it assumes that the set 1 through n can be written as a partition a, b, which doesn't need to be known to the algorithm, such that the sum of wi tau I for I and a is at most the sum of the same thing for I and b. In other words, the weighted sum of the tau is weighted by w. The contribution to that from a is at most the contribution of the same thing from b. Then the algorithm outputs a new set of weights w prime, which are also non-negative, satisfying two things. So first of all, I should say as well, I'm assuming that the original set of weights is not identically 0. And then the algorithm guarantees that the support of the new set of weights is strictly contained within the support of the old set of weights, and I should emphasize this is strict containment. So in other words, the indices in which w prime I are non-zero is strictly contained within the set of indices where wi is non-zero. So that's the first guarantee. The second guarantee is that w prime removes more weight from b than from a. In other words, the mass removed from a is the following quantity, wi minus wi prime, and the claim is that this is strictly less than the same thing for b. So let's prove this. It turns out that the update that achieves this is actually very straightforward. It simply does the following. So it forms tau max to be the max of tau I for I being in the support of w. And then it simply lets w prime I be 1 minus tau I over tau max wi for all I. As a brief side note, note that this is a very simple update algorithmically. In particular, it can be done in linear time. Let's actually prove that it satisfies the conclusions of the lemma. So first of all, notice that certainly the wi primes are all non-negative and upper bounded by wi. To prove the containment of the supports, notice that first of all, the support of wi prime is clearly contained in the support of wi. Just because if wi is 0, then wi prime is 0. To prove the strict containment, notice that if I star is any index that achieves this argmax here, then certainly we have that wi is greater than 0 because I is in the support of w, but by the nature of the update, wi prime is equal to 0. So this proves that the size of the support is strictly decreasing. Okay, to prove the second thing, which is that we remove more mass from B than A, let's just write out what these things are. So let's just write out what sum for I and A of wi minus wi prime is. Well, this is simply wi, let's just plug in the update, 1 minus tau I over tau max wi, and this simplifies very nicely to get 1 over tau max sum I and A of wi tau I. Okay, and if you do the same manipulation for I and B of wi minus wi prime, you just get 1 over tau max times I and B of the same quantity. And notice that very conveniently, we made the assumption that this sum is less than this sum. So that proves B. So with that primitive, we can now actually state the entire multivariate filtering algorithm that will achieve the right error. The algorithm itself is actually very simple, and it works directly from the intuition from the spectral signatures lemma, which, if you recall, says that it suffices to find a set of weights in in this fancy W set, such that the sigma of W has bounded spectral norm. So then the algorithm does the following. It's an iterative algorithm. It maintains a set of weights, initially set to be the uniform weights over everything. And then while sigma of Wt, my current iterate, has too large of a spectral norm, so the spectral norm is at least C, where this C is like, you can think of it as some constant, but it can be any constant strictly bigger than 1. So this is just something which is theta of 1. So while this happens, I do the following. I simply downweight points by their contribution to the spectral norm. So formally, I let v sub t be the top eigenvector of sigma Wt. And then I let the taus be the following univariate scores. I'll explain like the reason for this exact form later on, but it's simply v sub t interprod xi minus mu of Wt quantity squared. And then I simply let Wt plus 1, the next iterate, be the 1D filter with this set of taus and my current set of weights. And I just repeat this process until the spectral norm is below this threshold C. And then at that point I output mu of Wt, the final iterate. Okay, before I actually explain why this is correct, let's notice why this is a polynomial time algorithm. So first of all, clearly each iteration can be done very naively in polynomial time because I can take top eigenvectors using something like SVD. And we previously argued that the 1D filter can be performed in nearly linear time. Moreover, we can't run for that many iterations, simply because in this step here, one of the guarantees of the 1D filter was that the support of Wt plus 1 is strictly smaller than the support of Wt. So after n iterations, we would have to have gotten rid of everything. Okay, so that means this inner loop can only run for like n iterations. So if you put these things together, you get some polynomial runtime. It turns out, I think we'll cover this next lecture, but you can actually do quite better, even by analyzing essentially the same algorithm, and that you can actually get a runtime for this algorithm of something like order nd squared. So recall that the time to do a pass over the entire data set is order nd, because I have n d-dimensional vectors. So this is saying that this algorithm takes essentially d passes over the data. More recently, actually, it was shown that you can actually do much better, but we'll actually get to that later. But just for future reference, it turns out you can actually do nearly linear time. So you can actually do O tilde of nd, which is kind of nice. Okay, so in the remainder of the lecture, we'll prove correctness. To do so, I claim it suffices to prove the following condition, which is that at termination, so at the very last iteration, we have removed more mass from the bad points overall than from the good points. So let me call this condition star. And this is simply that the sum of 1 over n minus Wti, where t is the very last iterate, this sum for I and s intersect as good is at most the same sum over I and S bad. So why does this suffice? Well, recall that at termination, we have the condition that W of t, or sigma of Wt, has spectral norm which is at most C, which again you should think of as some constant. Moreover, I claim that this condition star, this implies that Wt is within script W of n comma 2 epsilon. So why is that? So notice that first of all this quantity is at most epsilon. This is because even if the Wti's are 0, the sum of I and S bad of 1 over n is at most epsilon. So that means that both quantities here are at most epsilon. But we have that W of S minus W in L1 norm. Well, W is always, this is Wt. But we always have that Wt is upper bounded by W of S because we're always removing mass from W of 0, which is W of S. So you can write this as simply I equals 1 up to n of 1 over n minus Wt of I. Okay, but I can break this into the two parts, I in S intersect S good of this sum plus the same sum over S bad. And this condition star implies that both terms are at most epsilon. So this overall is at most 2 epsilon. So it says that Wt is within this script W set. But then the spectral signatures lemma immediately implies that mu minus mu of Wt now 2 norm is at most something like 1 minus 1 over 2 epsilon times square root of 4 epsilon plus square root of 2 epsilon c. And so notice that as long as epsilon is less than 1/2, this is something like order of root epsilon. And that's it. So this says that really all it suffices to prove is this condition star. We'll actually prove something stronger, which is that in every iteration where we don't terminate, we always remove more mass from the bad points than the good points. So formally, in every iteration t where we don't terminate, we have the sum of Wti minus Wt plus 1i over I and S intersect S good is always strictly less than the same sum for I and S bad. It's not too hard to see that by induction this implies the previous claim, simply because W of 0 is equal to W of S, the uniform set of weights over everything. So let's just establish this stronger claim. So let's focus on one iteration where we don't terminate. So we're at some Wt, and we know that sigma Wt has spectral norm which is strictly greater than C. So how do we show a guarantee like this? Well, recall the way that we form Wt plus 1 from Wt is we call this 1D filter with these scores tau, given by that formula I showed you. So the way we reason about 1D filter is through that lemma that we proved. So let's just call this set A. Let's call this set B. So know that A and B form a partition of 1 through n. So the lemma for 1D filter says that it suffices to show the following, that the weighted sum of the Wti tau i's for I in S good intersect S is strictly less than the same sum for I in S bad. So this is what we're going to prove, and we're going to demonstrate this inductively. So we're at some iteration, and this claim is held for all iterations previous to this iteration. And now we just need to show that it continues to hold. So in particular, notice that this invariant that we get to inductively assume implies that at this current iteration, the Wt has a property that I remove less mass from the good points than the bad points. So in particular, let me just say that this inequality here star holds at this current iteration. So we get to assume that star holds at t, but that sigma Wt has spectral norm which is too large. Okay, and now for the rest of the proof, let's just drop the t's notationally because we're only going to focus on this one iteration. So now at this point, this is where we need to actually use the definition of the tau i's. So recall that the tau i's have the following form. It's v inner product xi minus mu of w squared, where v is the top eigenvector of sigma w. Recall we're dropping all the t's. And we get to assume this fact that the spectral norm of sigma of w, which I can also write as v transpose sigma of w, v is at least c, just because v is the top eigenvector of sigma w. So what we need to show is the following fact, which is that I just replaced the tau i's in the previous statement with just their actual forms. And now we can actually kind of see why we chose tau I to be of this form. Notice in particular, if we sum the left and the right hand sides of this inequality, we just get the sum over all I and s of wi times v inner product xi minus mu of w squared. And if you just stare at this for just like a couple of seconds, you'll see that this is actually just v transpose sigma of w v, which is by the definition of eigenvectors, simply the spectral norm of sigma of w. So in other words, these tau i's actually tell you exactly how much each individual point contributes to the spectral norm of sigma w. And this is really convenient because now we can actually do a lot, because in this expression again here, we know that both the left and the right hand side are non-negative, and they sum up to the spectral norm of sigma w. So in other words, to show that the left hand side is at most the right hand side, it suffices to show that the quantity here on the left hand side is at most 1/2 of the spectral norm of sigma of w. Okay, so this is what we're going to show now. So let's just write this out again. And let me just do the following kind of dumb looking inequality, which is just to note that each one of these summands here, the v inner product xi minus mu of w squared, is non-negative, and each wi is at most 1 over n. So I can upper bound this sum by just replacing the wi's with 1 over n. When I do so, I get this expression here. And now all I'm going to do is I'm going to recenter at mu instead of mu of w, just by adding and subtracting mu from every expression here, and noting that mu is the mean of the points that I'm summing over, because again, mu is by definition the mean of the points in S good. So when I do this, I get that this sum actually becomes the sum of two things, so these two terms, which I'll call 1 and 2 respectively. Okay, so now let's upper bound each one of these terms separately. Upper bounding 1 is actually really straightforward, because this is actually just v transpose times the covariance of the good points, v, but we assumed that the covariance of the good points has spectral norm at most 1, and v is a unit vector because it's a unit eigenvector. So that means that 1 is upper bounded by 1. Okay, so now to upper bound the second term, we're actually going to invoke the spectral signatures lemma one more time. And here, the reason why we can invoke the spectral signatures lemma is because we have that this w is in script w of n comma 2 epsilon. And the reason why that's true is because we know that in every iteration so far, we've removed more mass from the bad points than from the good points. This is the inductive hypothesis. And so we have this, so we can apply the spectral signatures lemma with an appropriate choice of parameters. And when we do so, we get this following upper bound here, which we can simplify. So this becomes 1 over 1 minus 2 epsilon quantity squared times 4, oops, that's not how math works, times 2 epsilon plus 2 epsilon times the square root of the spectral norm of sigma w plus another 2 epsilon times the spectral norm of sigma of w. Okay, and overall we want this entire expression, so 1 plus 2, to be less than or equal to the spectral norm of sigma of w over 2. So let's see why this is true. Well, the first term, certainly if I take c to be sufficiently large, so recall that we assume that this is at least c over 2. Certainly if c is sufficiently large, then the first term will not contribute anything. To show that the second term will not contribute anything, notice that there are terms here that depend on the spectral norm of sigma w, like this term and this term, but both of them are multiplied by coefficients that depend on epsilon. So as long as epsilon is sufficiently small, you'll always get something which is less than the spectral norm of sigma w over some like arbitrarily small constant. So putting that all together, you'll get that the sum of these two things is less than sigma w over 2, the spectral norm of sigma w over 2, and that concludes the proof. So in other words, that shows that we have this invariant here, that in every iteration we remove more mass from the bad points than from the good points, which in turn implies the following invariant, that we remove more mass from the bad points than the good points at termination. And again, that was all we needed to show that at termination we output something good, thanks to the spectral signatures lemma. I personally find this slightly magical, because it really doesn't feel like we've proven anything this entire lecture, at least to me. But really all the work went in lecture 4, in the proof of the spectral signature stuff. And this is all just kind of using corollaries of that. So that completes the proof of correctness of the algorithm. Let me just flash a formal-ish statement of what we proved, but hopefully it's pretty clear that if we have an epsilon crypto set of points for epsilon sufficiently small, where the good points have bounded covariance, then we can output an estimate of the mean of the good points to error up to constants root epsilon. Okay, and moreover this runs in polynomial time. Okay, so that's pretty cool, and that's a pretty good starting point, but there's a lot that we can do. And in the next lecture, we'll actually go into this. We'll go into this in 2 ways. So first of all, we can improve the breakdown point a lot. So right now we need epsilon to be less than some relatively small constant. I think when I worked it out, it was something like 0.1-ish. But you can actually do much better with a very small tweak to this algorithm. Another thing is the runtime. While it is polynomial, it currently requires like n iterations, where each iteration requires a full SVD, which is kind of slow. In the next lecture, we'll actually show as well that you can optimize this much further, down to, as I mentioned earlier, order n times d squared. And as I also mentioned earlier, later on in this course, we'll actually show, by using more advanced techniques, how to get a much better runtime of O tilde of nd. So, nearly linear time. Okay, so that's it for today. See you.